The celestial star is far outside the small star belt. Located between Saturn and the celestial star. It travels alone on the dark and cold edge of the solar system. Its rotation axis is extremely tilted, almost lying horizontally on its orbit. This ordinary posture has long puzzled astronomers. Giving rise to countless theories. In 1781, British astronomer William Herschel first discovered this planet. The celestial star is the first planet discovered by telescope. This discovery expanded human understanding of the solar system's boundaries. For centuries, this distant planet was merely a faint point of light in telescopes, like a blue, ghostly sphere. But now, with the advent of the James and Webb Space Telescopes, the exploration of the celestial star has ushered in a new chapter. The Webb telescope, with its unprecedented observational capability, gradually unveiled the layers of this celestial star, showing a beautiful and complex world. The high sensitivity of the Webb telescope allows us to clearly observe Uranus's atmosphere, meteorological patterns, and even its mysterious ring system. By analyzing Uranus's spectrum, the Webb telescope can interpret its atmospheric composition, detecting the presence of gases like methane and hydrogen. This not only helps us understand the current state of Uranus, but also provides clues about its formation and evolution. James, the Webb Space Telescope continually exceeds expectations, revealing new cosmic details for us almost every day. Its latest achievement is a set of newly captured images of Uranus, which even surpasses the stunning observations from April 2023. At the beginning of 2023, the Webb telescope allowed us to see Uranus's atmospheric dynamics and ring system with unprecedented clarity. The latest images go further, not only clearer, but also revealing details that were previously unobservable. Using Uranus's rings as a force, the latest images display more astonishing structures, even capturing unprecedented features. For example, the extremely thin C ring closest to Uranus. The advantage of the Hubble Space Telescope is not only in one-time observations, but also in its ability to continuously track changes in celestial bodies. Continuous observations of Uranus enable us to track changes in its atmosphere, record the movement of clouds, and even observe the long-term evolution of storms. In particular, changes in the polar regions of Uranus are especially noteworthy. The bright white cap near the poles and the dark banded areas have undergone significant changes in recent years. These continuous observations provide valuable data for understanding Uranus's seasonal changes and long-term climate patterns. Among the planets in the solar system, Uranus stands out with its unique features. Its rotation axis tilted about 98 degrees, almost parallel to the orbital plane. Uranus's nearly horizontal rotation posture has long attracted astronomers, stimulating their interest in exploring its causes and impacts. Scientists speculate that, in the early formation of the solar system, Uranus's tilt was not so extreme. Mainstream theory holds that it may be a catastrophic collision, perhaps colliding with a planet-sized celestial body, completely changing its rotation direction. This huge impact not only changed Uranus's rotation axis, but also left a profound mark on its entire system, including the satellite and ring systems. This unique tilt leads to Uranus's poles, alternating bathing in sunlight or falling into darkness every 42 years. This extreme tilt brings extreme seasonal changes, which are completely different from the seasons observed on other planets. For planetary observation and research, this unique perspective brought by the tilt is crucial. It allows us to observe Uranus's rings and satellites from different angles, revealing their composition and dynamics. For example, when Uranus's rings face Earth, the rings are almost completely invisible, exposing the darker belts and smaller satellites. In contrast, Earth's rotation axis tilt is only 23.5 degrees. The extreme tilt of Uranus causes significant weather changes, making it a valuable subject for planetary climate research. This tilt also affects the circulation of Uranus's atmosphere, with the poles exposed to sunlight for long periods, forming complex weather systems. The latest images captured by the Hubble Space Telescope show these systems are completely different from those on other planets, providing a unique experimental site for our understanding of atmospheric physics, allowing us to traverse a year on Uranus together. Since Uranus takes about 84 Earth years to orbit the Sun, each of its seasons corresponds to 21 Earth years. Thus, each hemisphere experiences long days and nights, leading to dramatic changes on the planet's surface and climate. One pole of Uranus endures summer under sunlight for decades, while the other pole is trapped in prolonged winter. This stark contrast brings about unique atmospheric conditions, forming complex weather systems and climate changes. These seasonal changes have profound effects on Uranus's atmosphere. When sunlight shines on the planet's surface, the atmosphere is heated, forming huge storms and active cloud systems. These phenomena are not static, but continuously evolve with the changes of the season, depicting a constantly changing appearance of Uranus. Most striking is the bright cloud tops. When the sun shines on Uranus's atmosphere, these clouds composed of frozen methane and other gases will reflect sunlight, forming a splendid landscape, while dark storm areas roam the planet's surface like huge hurricanes. In addition, Uranus's seasonal phenomena affect not only itself, but also impact its satellites. A recent study found that Uranus's satellites can form temporary atmospheres under specific conditions. This phenomenon is closely related to Uranus's unique environmental conditions. The key to forming these temporary atmospheres lies in Uranus's extreme axial tilt and its influence on satellite orbits. As Uranus's satellites orbit the planet, they undergo long periods of intense sunlight and long periods of darkness. During the prolonged summer, the frozen surfaces of the satellites experience sublimation, directly from solid to gas, forming a thin temporary atmosphere. These atmospheres are most prominent when the satellite is warmest. Recent studies indicate these atmospheres are more complex and variable than previously thought. Uranus's satellite rings are often overshadowed by the spectacular Saturn rings, but they also possess unique cosmic mysteries. Recent comparative studies of Uranus, Saturn, and Jupiter's rings reveal these relatively unknown, but equally captivating celestial features. Unlike Saturn's wide and bright ring system, Uranus's rings are narrow, dim, and limited in distribution, extending within 4 planetary radii, including some difficult-to-observe rings, such as the Epsilon ring and the Nu ring. The research delves into the gravitational influence of Uranus's main satellites on the ring system, a factor that plays a key role in the formation and evolution of the rings. Uranus's 5 main satellites, Miranda, Ariel, Umbriel, Titania, and Oberon, are larger than other small satellites, dominate the gravitational structure within the Uranian system. Their mass and position provide us important information for understanding Uranian satellites and their gravitational formed ring systems. The formation of Uranian rings is believed to be the result of multiple processes, including collisions, satellite breakups, and gas release from major satellites. These dynamic processes affect the material composition of the rings and are driven by the constantly changing environment of the Uranian system. The stability of the ring system is closely related to the gravitational interactions with satellites. Research also explores the material bombardment processes within the ring system and the important role of shepherd satellites in the maintenance of the ring system. Uranian rings also provide us a unique opportunity to study the internal structure of planets through seismology. Model results indicate the gravitational interactions between satellites and the ring system can lead to significant material loss in the rings. The complex interactions of these satellites with the ring system, the mysteries of Uranus, are not limited to this. As is well known, there are auroras on Earth, and auroral phenomena also exist on Uranus. However, its auroras mainly appear in the infrared spectrum. Through observations with faint telescopes, astronomers detected enhanced radiation of trihydroxyl ion H3+ in Uranus's atmosphere. This is a groundbreaking discovery, which helps reveal Uranus's unique magnetic field and atmospheric dynamics. Uranus's magnetic field is severely tilted relative to its rotation axis, forming a unique magnetosphere, coupling between the ionosphere and thermosphere. These observations of infrared auroras are very crucial. They open a new window for us to explore the dynamical science of Uranus's magnetosphere. Uranus's infrared auroras exhibit significant differences from those of Jupiter and Saturn. On Jupiter, the lifetime of Lich ion radiation is relatively short, causing the changes in ultraviolet radiation to be relatively stable. However, the brightest infrared radiation of Uranus does not necessarily correspond to the brightest ultraviolet radiation of other planets. This auroral feature provides us with rich information about planetary atmospheres, which is particularly beneficial for the study of ice giant exoplanets. In-depth studies of Uranus's auroras show that the hotspots near the auroras are not caused by temperature increases. The task objectives include studying Uranus's unique magnetic field, complex ring system, and atmospheric dynamics and internal structure. Fortunately, the Uranus Orbiter and Probe mission have been listed as the highest priority flagship mission of the 2023 to 2032 U.S. planetary science decadal survey. The expected launch window is between 2030 and 2034.